Section 11.2 is about series. So we've been talking about sequences. Those are lists of numbers, which you can write by sort of writing the first few elements and then a ... or you can write in closed form with brackets. A series, on the other hand, is not a list of numbers, it's a sum of numbers. Again, an infinite sum, so A1 plus A2 plus A3, etc. We will often write series using sigma notation. So this means add up the A sub n things, starting at n equals 1 and going forever. If I only wanted to add up to a certain point, I would put the subscript for the last one I wanted to add on top. So the sigma there, the sum from n equals 1 to 7 of an would be a1 plus a2 plus a3 plus a4 plus a5 plus a6 plus a7. But generally, we'll want an infinite series, so the infinity symbol will be on top. Okay, great, but that doesn't seem to make sense, at least to many people. How can you add up infinitely many numbers? We're used to adding 2 numbers, and usually we can add like 6 numbers by, starting with 1 and adding the next one to it, and then adding the next one, and then adding the next one. So we're always just sort of adding one more number at a time. But how can you find an infinite sum without just adding forever? Well, one way to think about it is we actually do this all the time. When we write things like pi equals 3.1415926 ... however many digits of pi you happen to know, we all know that that never stops. Pi is an irrational number, so its decimal representation never stops and never repeats itself. But what does that mean? That means pi is 3 plus 0.1 plus 0.04 plus 0.001 plus 0005 plus 0.00009 plus, and that could go on forever. And that is an infinite list of numbers that we're adding up, and they equal this number pi, which is smaller than 4, right? It's a finite number. But the addition goes on forever, right? And it doesn't really bother us because we're used to it when it's written in the sense of an infinite decimal, but it really is the same as this infinite series. Or here's another example. Everybody believes that 1/3 is equal to 0.333333333 forever. But again, I can break that up. 0.3 plus 0.03 plus 0.003 plus 0.0003, etc. forever. And those I can write as 3 over 10 and 3 over 100 and 3 over 1,000 and 3 over 10,000 and so on. And that gives me a way to sort of write this in a formulaic way using sigma notation. That is, all I'm doing is adding up 3 over 10 to a power, starting with the power 10 to the 1, and then add 3 over 10 to the 2, and 3 over 10 cubed, and 3 over 10 to the 4th, and keep doing that forever, as indicated by the infinity on top. So this is really an infinite series, and we have no trouble believing that it equals 1/3 when we write it as 0.3333333 forever. We have to keep adding forever because if those 0.333, if the 3's ever stop, it's not actually exactly 1/3, it's just a little bit less. So it really does take adding forever to equal 1/3. So, in particular, any non-terminating decimal really is an infinite series. And it's got a finite sum. So we should have no trouble believing that you can have these infinite additions that add up to a finite sum, finite number. Another way to think about this is an ancient Greek guy named Zeno. I don't know if that was his real name. Some of these ancient Greeks like to sort of take, street names, philosophy names. So Zeno's paradox, he had a few of them, but here's one of them. He said, okay, suppose I want to walk from where I am to the other side of the room. In order to do that, first I have to walk half of the way. Then I'm halfway across the room, and then I have to walk half of the way from where I am then to the other side of the room. That's 1/4 of the room. Okay, so now I'm 3/4 of the way across the room. I have to walk half of the remaining distance, that's 1/8 of the original, and then half of that remaining distance, which is 1/16 of the original, and so on. So at every point where I am located, I still have to walk, before I can get to the other side of the room, I have to walk halfway there. And if you just keep adding up all those halfways, you get this infinite sum. And Zeno said, well, that means I have to cross an infinite number of positive distances, right? I have to cross halfway across the room, and a fourth of the way across the room, and an eighth of the way across the room on top of that, and a 16th of the room on top of that. And all of these distances are non-zero, they're positive, and there's infinitely many of these things that I have to cross before I can make it to the other side of the room. So I'll never make it. I can never get to the other side of the room. Well, Zeno, of course, was not dumb. He realized that he could, in fact, walk to the other side of the room. He did it all the time. But this paradox bothered him and was discussed. How are we crossing infinitely many distances when we cross a room? Right. The idea now, the language we use now, would say, well, crossing those infinitely many distances is adding up this infinite series, and we will see that such an infinite series has a finite sum. All those half plus a fourth plus an eighth plus a 16th, etc., added up forever actually equal to 1, the total 1 distance from here across the room. And so you can do it. Okay. So what's the general idea? Well, we have a sequence of terms, A1, A2, A3, and we'll start adding them up to create the infinite series, A1 plus A2 plus A3 plus A4, and so on, written out or written in sigma notation. And the question is going to be, under what circumstances does that infinite addition problem have a finite sum? And what does that even mean for that infinite addition thing to add up to a finite number? The way we will deal with this is to make a new sequence called the sequence of partial sums. So we have the original sequence with the terms in it, A1 and A2 and A3. When you add those terms together, you're creating the series. And now to analyze the series, to decide whether it has a finite sum or not, we will make a new sequence, the sequence of partial sums. So what is this sequence? Well, the sequence of partial sums is notated with S subscript n instead of A subscript n, like the terms of the sequence or series. So sums with S's. And it's a sequence, S1, S2, S3, S4, and so on. And what are those numbers? Well, they come from the series. So S1 is just the first term. S2 is what you would get if you took the first 2 terms and added together. S3, the first 3 terms. S4, the first 4 terms, and so on. So S1 is A1. S2 is A1 plus A2. S3 is A1 plus A2 plus A3, and so on. So in general, SK means take your series, add up the first k terms, and then stop. Don't keep going forever. Right? So we can write that in sigma notation like so. But these are partial sums, right? The whole series may or may not have a sum, but it has all these partial sums. So S17 means add up the first 17 numbers in your series and then stop. Okay, so as the n gets bigger, Sn is adding up more and more and more terms of the series, going farther and farther out. It is important to keep the difference between these things clear. So there's the series, there's the sequence of terms, and there's the sequence of partial sums. Let's look at an example. So if I have the series, it looks like this. That's the sum, n equals 1 to infinity of 1 over n. That is, start with 1 over 1, and then add 1 over 2, and then add 1 over 3, and then add 1 over 4, and just keep going forever. Okay. The sequence of terms is those individual numbers you are adding. 1, 2, 1, 1/2, 1/3, 1/4, etc. Right, the sequence 1 over n. So just turn the pluses into commas, and you've gone from the series to the sequence of terms. The sequence of partial sums, on the other hand, is what happens when you add up the numbers in a series but stop after a particular amount. So the first partial sum is 1, because that's the first term. The second partial sum is add up the first 2 terms, 1 plus 1/2. That adds up to 3/2. The third partial sum is add up the first 3 terms, 1 plus 1/2 plus 1/3. That adds up to 11 over 6, and so on. So the sequence of partial sums starts off 1, 3/2, 11/6. If we worked really hard, we could come up with a formula for SK. That is, what would happen if you add up 1 plus 1/2 plus 1/3 plus 1/4 all the way up to 1 over k. Right? But these are three different things. There's the sequence of terms, the series, and the sequence of partial sums. So why do we care about these partial sums? Well, they are what tell us what happens to the series. So given a series, you look at the sequence of partial sums. If that sequence, the sequence of partial sums is a sequence, if it has a limit, if it converges to a finite limit called S, the sequence of partial sums converges to a finite limit called S, then we say the series converges and its sum is S. If that sequence of partial sums diverges as a sequence, there's no limit or the limit is infinity, then the series diverges. That means adding up those numbers forever won't give you a finite answer. Right? So if the sequence of partial sums converges to a finite number, adding up the series forever gives you that finite answer, and the series converges. Otherwise, the series diverges. So when we say that this infinite series adds up to S, what does that mean? It means we can get answers as close to S as we want by just adding enough terms of the series. So as you add up more and more and more terms of the series, you get closer and closer and closer to the sum S. So for example, back to the beginning thing, 1/3 is 0.33333, which we wrote as this series. What that means is by adding up the terms from n equals 1 to 10, I can get really close to 1/3. If I add up even more terms, n equals 1 to 50, I get even closer to 1/3. And I can get as close as I want to 1/3 by just adding more and more and more terms of this series. In general, it's a very hard question to figure out whether a particular series converges or not, and if it converges, what its sum is, right? You look at the sequence of partial sums and you analyze it, but that can be quite challenging. What we will be doing in this class for the next several sections is learning and using some techniques to apply to series to tell if they converge or not. So here's your video question to work out and bring to class. I have a series. Its terms are -1 to the n over n squared, starting at n equals 1 and going forever. I would like you to write the first 3 or more, if you feel like it, terms of the series, and the first 3 or more terms of the sequence of partial sums. So I want you to write out the terms of the series, and I would also like you to write out the first 3 partial sums, or more than 3 if you feel like it. Alright, I will see you in class. Bye.